this is top view of the filter controls. And goodness, there's a lot going on here. So you know where we're at, right? We've gone and we've looked at this set of controls, and we're going to try to figure out how they work, because there is a lot going on. So let's follow the water. So the water, remember, magically, because I haven't drawn this yet in the design, but magically, maybe we'll use Bluetooth, the water from the clarifier ends up in this channel. Come on, only a couple of you even smiled about using Bluetooth to transport the water across the plant. Okay, so we'll get the water into this channel, and then this channel serves all the filters. And in order for the water to get into one of the filters, it has to cross a wide weir. I should have said wide weir. It's quite wide, and the water flows across that wide weir, and we're counting on that wide weir to distribute evenly the flow between the two filters. So one filter gets its water over this wide weir, and the other filter gets its water over this wide weir. Then there's this intermediate channel that has water in it. That's now the flow rate of water for one filter, or in this case, half the plant flow rate is going to each filter. So half the plant flow rate is sitting in this channel. And this little pipe is connected to a plate that is covering up a little slot weir. So there's a narrow slot that the water flows from this channel into the inlet box for the entire filter. And the reason for that this channel, or one of the things that this little channel, intermediate channel does, is if we, for any reason, need to bypass the filter, we put this, we shut the slot weir, right, by putting this plate in front of it, and we would pull this pipe stub out, and now water can come from this inlet channel, go into this intermediate channel, not go into the filter box, in the inlet box, but instead kind of cheat and go right to the outlet. And right here is the pipe that would go to the distribution tank, the clear well, and onto the community. So instead of going through the filter, it's just bypassing. Okay, so I covered the bypass, but that's hopefully not going to be used very often. The real path is to go through this slot weir and then into this inlet box that has 4 pipes leading out the bottom that are going into the filter, and a 5th pipe that is an overflow. So when the water level gets too high, this overflow kicks in and it starts dumping the excess water so that the plant doesn't flood. The water goes into the filter through those 4 pipes and then pops back out of the filter through these 3 pipes. So the water level down here is much, much lower. And the water flows over a tiny weir. So this is a very low weir that the water flows over and goes into this final filtered water spot that is shared by 2 filters. So water is going across the weir in this direction. It's also going across the weir in this direction from the filter on the right. This pipe here will hold a flexible tube that is dripping chlorine. So the chlorine from the dose controller will end up in a flexible tube that will dump out right here, and water will be flowing down into this pipe and leaving to go to the clear well. Okay, I want to take you down another path yet. What do you do when there's enough water, maybe when the flow rate to the plant has reduced by 50%? How do you make it so that you can just easily backwash one filter? So here's where we play an interesting trick. If there's only enough water to backwash one filter, during backwash, you would like all the water to go to that one filter, right? And the way it's set up right now, there's this broad weir here, or wide weir, and there's one here as well. And that weir is what's controlling the flow to the filter. And since they're both the same, half the water goes across each weir. And so we're not having any way to actually get, we'd like all the water to go to one filter during backwash. So when you want to backwash under low flow conditions, what you do is you remove this gate. So this is another one of those plates that just is held in place on this, at this weir, and you just lift that out. And when you do that, it opens up a much bigger opening into this filter. And now that filter is going to grab, well, what's going to happen is the water level in this intermediate space is going to end up being the same as the water level in this channel, because you opened up this big opening. So the water level here and the water level here is going to be the same. And now we've switched the control point for the filter. Now this narrow weir is designed so that it can handle the design flow rate. And so it will deliver the design flow rate to this filter. Wow, did that make any sense? I changed the point of flow control. It used to be that the flow was controlled by flowing across this weir. And then I basically disabled one of the weirs. I blasted a big hole in it so it gets all the water. And now our second control takes over, and that's this narrower weir that's taller. It's designed to just handle the flow rate that you need for the design flow rate. And so it will ensure that you don't get too much water in the filter to backwash it. And it'll, if there's only half design flow in the plant, it'll take all of it if there's two filters. And the other filter will be high and dry and get nothing during backwash. Okay, here's another thing. This is going to make more sense later on, but there is an extra orifice that's tucked into the inlet that is the backwash inlet. And this is complicated too. This is about making sure that the same amount of water goes in the backwash inlet, the bottom inlet into the plant, into the filter, as what goes in the top inlet under conditions of filtration. So we needed the kind of the loss coefficients or the head loss flowing through the top pipe and the bottom pipe to be the same during filtration. And so but you already know that the backwash pipe is often bigger, and there's some other differences too, because it has to be able to handle the backwash flow, which is all the flow during backwash. So it has to be bigger and there has to be less head loss during backwash, but we needed to have more head loss during filtration so that it's the same as this top pipe. And so the way we adjust it is we add some head loss, we add an orifice during filtration so that it doesn't get too much water during filtration. Somebody want to ask a question about that one? So if I didn't do anything during filtration mode, the bottom of the filter would get too much water because I've designed the bottom path to be less head loss so that, or it's bigger capacity because it's got to handle the total flow of the plant or total flow of the filter when we're doing backwash. Here are a couple slices now, section views, looking at the side of the filter. In this view, we're inside the inlet tank. And so you can see the 4 inlet pipes going down and dumping water into the filter. And so here we can see inside the filter, and we can see that there's complexity inside the filter as well. Okay, so we see the water going in, water going out. Oh, okay, and there's sand. Okay, so if there were sand there, you wouldn't see anything. So happily, I didn't draw the sand, but I put some sand in there just for show. And during that's the height of the filter sand. During backwash, it's going to expand. We estimate about 30%. So that means that our pi backwash over filter is the backwash height of the sand divided by the filter height of the sand. So that number is like 1.3. 1.3 minus 1 is 0.3. So there's this extra height of sand that happens when you're backwashing and the sand is fluidizing. And you'll notice that the pipe, the siphon pipe that takes the water out during backwash is above that level to make sure that we don't take sand out when we're backwashing. And then you also know that the head loss through the sand when you're backwashing is roughly equal to the height of the filter sand. So there must be another height of the filter sand up here, and the water level coming in this box must be higher than that, so that there is enough potential energy in the water in this inlet box to fluidize the sand and then leave through this the siphon pipe. And the siphon pipe, I'll trace it in one of the next drawings, but it ends up over here, exiting right at this level. So you can see that there's more than the height of the sand between the water level in this tank when it's backwashing, which is right up here, and where it exits from the siphon. And that energy we need, because we're going to lose that energy fluidizing the sand bed. Here's a cross section through the filtered water tank. So now this is at a different layer. I'm slicing it again. Here we can see that all of these three pipes are bringing the filtered water out. So they're if this top one is 1, they are 2, 4, and 6. Pipes 2, 4, and 6 are the outlets, and they get out of the way by going through a 45-degree bend here, and then they shoot up and go into this outlet box. And do you see that each of those outlets serves exactly 2 layers? Why was I holding up 3 fingers? How about 2? Each of those outlets, each of those 3 outlets is serving exactly 2 layers, because there are 6 filter layers total. If we go back 1, here, each inlet, these inlets do different things. Look, the top inlet serves 1 layer. The bottom inlet serves 1 layer, but the middle 2 inlets, the inner 2 inlets, water can go either up or down. And so they each serve 2 layers. So you're seeing that, these pipes are not all the same. Some of these trunk lines serve 2 layers of sand and some serve 1. Okay, now we're looking at the siphon pipe. This is the pipe that takes the water out of the filter box when we are backwashing. So there are some orifices that you can just barely see here that are on the top of that pipe. They're taking the water out. It goes through, it's a siphon, and we'll learn more about that maybe today. And it discharges right here. And if you look at this pipe, there's something mysterious about it. There are no valves in this pipe, and yet under normal operation, the water level in the filter is up here somewhere. And so the question is, why isn't that siphon pipe just always emptying the water out of the filter? And we'll figure out what the magic is of that eventually. We can also go into the filter box. So inside the filter box, there's a ton of stuff. So this is an end view. Here's where the inlets and outlets and inlet and outlet and inlet and outlet and backwash inlet would connect into this system of the internal plumbing. This doesn't show everything, but it shows a lot of the pieces. These pipes here are receptor pipes. These pipes are branches, and these pipes here we call trunks. And then there are these hose clamps that go around one whole bundle of two receptors, the branches, and a trunk. These hose clamps hold it all together because this whole system can be disassembled. It's not glued together. So here are two other views of this same mess of plumbing. Yes, so you can see here that the inlet pipes have holes in them. And I'm not showing everything in this view. I'll show more. Well, let's go to the next slide just for a second. Inlets and inlet branches look like this. So I'm not showing everything in the previous drawing because that's still under construction from my perspective. But each of these white, and actually this gray one as well, these branches with holes in the bottom don't look like what I've shown there. They look like this. So there's a pipe with holes in the bottom, and then there's this wing, which is exactly half of a pipe that's glued onto the main branch. And wow, and its role is to prevent sand from getting into those orifices when the filter is in backwash mode. So water is normally flowing out of these holes into the sand. So that should be fine. There shouldn't be any sand migrating up into these holes during filtration mode. But in backwash mode, it would be just too easy for some sand to get up into this pipe. And so to protect the pipe from getting any sand in it, we add this wing on the bottom. And then when backwash is happening, if you think about what's happening, you can imagine this being a fluidized bed of sand, and water is coming up through here. I should have drawn lots of arrows. Water is going up through the sand to keep it fluidized. And that would mean that the sand would be everywhere. But in here, inside this hemisphere, or what is this? This half cylinder, there's no upflow velocity, right? There's no water going up through that pipe. So the upflow velocity in here is 0. And that means that any sand that gets into this zone has a terminal velocity that the sand has, and it settles back out. And so this zone underneath this half pipe remains clear. And so there's no way for sand to get into this pipe. But I'll show you the other kind of branch, so you see how these work. These are the outlet branches. Here the water is going from the sand into the pipe. And the way that we prevent the sand from getting into the pipe is we have pipes that have 0.2 millimeter slots cut in them. I don't know if you've thought about 0.2 millimeters lately, but I think it's pretty similar to the thickness of your thumbnail. You can go check that on the internet and see if I'm right. But it's like you have to work to get your thumbnail into these slots. Okay, so really thin slots, so thin that the sand can't get in. And so this is the same system that is used in wells, where if you have an aquifer that's got sand in it, you can put a well screen that is just PVC pipe with these slots in it, and that will prevent the sand from your aquifer from getting into your well, and you'll have clean water in your well. So we're using that same idea inside the filter. Remember I told you I was thinking about what we're doing inside this filter like a well field with lots of wells in it. So here's one of my wells. It's got a well screen. Literally, it is a well screen. And here's another detail. Look at this. There's this crazy molded curve on the end of this pipe. That molded curve is going to connect to this receptor pipe out here. So here's the receptor pipe, and the branch fits into that receptor pipe, and the curve of the receptor pipe matches this crazy curve here. So the hole in the receptor pipe is drilled to be exactly the same diameter as what I have my mouse on. And then this branch slides into the receptor pipe and it hits everywhere at once along this curved surface. Why did we do this? Well, we wanted a positive stop for one, so that because we're going to hold this together with a clamp. And we need this branch to not rotate. Because if this branch rotates, the wing won't be doing any good. The wing has to be pointed down in order for it to work. So if the wing were pointed up or to the side, it's not going to work anymore. So we have to keep this branch from rotating, and it's that curved surface that keeps this branch from rotating. That's one. Then here's the slotted pipe. Slotted pipe also has that same shape on it. And my question to you is, can you think about why? Is there any reason why you wouldn't want a slotted pipe to rotate? Like, who cares which way the water enters this pipe? But it actually matters. Anybody think about properties of a slotted pipe? I wish I had one here to show you. If I had a slotted pipe in my hand and I went like this to try to bend it, in one direction, I can bend it really easily, and I turn it 90 degrees and I can't bend it. The orientation that we see with it in the top one, with the slots on the side, you can't bend it vertically, but you can bend it horizontally. That makes sense? I've made a weak structure into one direction. And what forces do these pipes have to withstand? At the beginning of backwash, all the sand is pushing up on these pipes, and they're going to bend, and they are going to bend. And so we need them to be full strength. And so we need the slots to be coming out the sides and the strength to be in the vertical direction. So we can't let these rotate either.